Hello, everyone. My name is Naichen. I am a PhD student from the University of Michigan in Ann Arbor. Today, I want to talk about our work on personalized principal component analysis. Suppose you are a manager of a factory for additive manufacturing. Your factory has multiple 3D printers. Each printer is equipped with some sensing technologies like laser scanners, thermal cameras, or simply some vibrational sensors. So you can collect data from these different 3D printers. And these printers, they are of the same type, but they may have their differences in their environmental factors, in their mechanical factors, in their process parameters, hyperparameters. So the signals can be different. At the end, we're facing a data set that is similar in nature, but has their heterogeneities. So to derive meaningful statistical analysis on such data sets, one might want to separate the common component among all these printers from the unique factors within each of these printers. Why? There are multiple benefits. The common factors are representative of the common knowledge shared among all these printers, and the unique components are indicative, perhaps, of the anomalies within each 3D printer. And both of these components are indicative of downstream analytics. They are useful perhaps in classification, in prediction, or in anomaly detection. Okay, so this small additive manufacturing factory example is representative of numerous statistical applications in healthcare, in energy systems, in transportations, etc., where we need to collect data from different heterogeneous but related sources. And it is important that we can have a systematic method to decouple the global component from the unique component so we can separate what is shared and what is unique. That is the goal for principle of a personalized principal component analysis. So for the rest of the talk, I will first introduce the mathematical formulation of personalized principal component analysis. And then I will introduce the identifiability conditions and try to set up an upper bound on the statistical error based on the identifiability conditions. Afterward, I will try to establish lower bound on the statistical error. And then I will introduce the algorithm to identify the principal components from the observations. And then I will use a few numerical examples to illustrate the applications of the personalized PCA in different scenarios. Since this is based on PCA, we can have a very high-level overview of this method, principal component analysis, which is an unsupervised statistical learning method for data dimension reduction and feature extraction. It has multiple applications in image processing, language processing, etc., etc. So to find the PCs that can explain the most portion of variance from data, one formulation is the constraint optimization problem formulated as equation 1, where the objective is the explained variance from the data covariance matrix S, and the constraint is the orthonormal constraint on the principal components. And we want to use the feature extraction capability and the interpretability of PCA to extract the common and shared features, the global and the global and unique features of data that come from different sources. A simple example is illustrated here, where we have data coming from two different sources, one labeled blue and another labeled pink. if we run standard PCA on this algorithm, we will recover two PCs represented as black arrows, one pointed up and one pointed horizontally. We can see that the black arrow that is pointing horizontally does not correspond to any PC of the dataset. Actually, it's an average of the PC from two different datasets. What we want the personalized PCA to achieve is on the right figure, where we have not only the black arrow pointing up, representing the shared PC, the global PC, but also the pink arrow and the blue arrow, which represent local PCs. Okay, so as a graphical representation of our model, we assume that we have data collected from n different sources represented as different square here with different color. And for source I, we assume that data from source I, observation yi, is driven by some global factors UG and some local PCs VI. If we write it down in equations, yi is driven by R1 global components and R2 local components and corrupted by some noise. The global component, the global PC, is UQ, and phi IQ is its coefficient. Local PC is VIQ, and phi IQ is its coefficient. This is a linear model, so everything has clear interpretations. The global PC, local PC, and their coefficients all have interpretations. An important assumption we make on top of this model is that the global PC and local PC, they should learn different things. They should capture different features and span different subspaces. So we assume that global PC and local PC are orthogonal. This is an inductive bias we add to the data generation process. Okay, so from the statistical perspective, our task is to recover the global PCs and local PCs from our observations. To do that, we can write everything into matrix form, concatenate them into matrices, and try to propose a constrained optimization problem here in equation 2. The objective is to maximize the summation of the explained variance on each data sources, where the explained variance is the projection of the covariance matrix on the subspace spanned by the global PCs and local PCs. The constraints require that global PC matrix to be orthonormal, the local PC matrix to be orthonormal, and the global and local PCs to be orthogonal. Okay, this is a very intuitive extension to the standard PCA formulation. It has been proposed in literature, but those algorithms in literature lack statistical and convergence guarantees. The first question we need to answer is that given our observation, can we actually solve the problem to recover the ground truth global and local PCs? Is it at all possible to obtain a good estimates of the solutions? It's a problem of identifiability. In centralized PCA, this question is answered by Eckert-Young theorem, which says the solution to the standard form of the constraint optimization problem of PCA, if it is not degenerate, if the covariance matrix is not degenerate, is the top eigensubspace of the sample covariance matrix. Okay, it has a unique solution and is denoted by the top eigenspace. However, this result does not directly translate into personalized PCA. We can look at a very simple counterexample where all the local PCs are also the same. In this case, The local PCs and global PCs can explain the covariance matrix equally well. It's very hard to differentiate which ones are local and which ones are global. Therefore, new conditions are required. So to this end, we introduce a notion called theta misalignment. So basically, theta misalignment characterizes the difference between the maximum eigenvalue of the average of the projection matrix onto the subspace spanned by the column vectors of the local PCs and 1. So we can prove that theta is always a constant between 0 and 1. Why do we call it a misalignment parameter? We can see this through a very simple intuitive example where there are only two sources, 1 and 2, and each source has only one local PC, that's V1 and V2. The angle between them is 2 times gamma, where gamma is a parameter between 0 and pi over 4. So by some calculation, we can see that theta, our defined misalignment parameter, is actually equal to the square of sine gamma. So when gamma is larger, the angle between two vectors are larger, the two vectors are more misaligned. Theta is also larger. The misalignment parameter is larger. That's why we call theta a misalignment parameter. So with our notion of misalignment, we're able to show a statistical error that says if we solve our constraint optimization problem to optimality, we can get a very close estimate to the ground truth. That means the difference between the subspace spanned by the solution, by the optimal solution, and the subspace spanned by the optimal solution, by the ground truth, is upper bounded by a statistical error. And this statistical error is dependent on the misalignment parameter theta, on the eigengap, which characterizes how a signal is different from the noise in the covariance matrix, and also the difference between the sample covariance and the population covariance matrix. Furthermore, if the samples follow a sub-Gaussian distribution, we're able to show that the upper bound on the statistical error will go to 0 as the number of samples approaches infinity. This basically indicates that our estimate is statistically consistent. Okay. So one may ask, is your statistical upper bound a proof artifact, or is the problem really that hard? So we will answer this question by showing a statistical lower bound that says basically our upper bound is tight up to some constants. Okay, I will skip the details of this proof, but basically we just construct a hard counterexample. Now it comes to solve the problem because our statistical upper bound requires us to obtain the optimal solution to this constraint optimization problem. But if you look at it, the objective in the minimization form is non-convex, and the constraints are also non-convex. So we're dealing with a constraint optimization problem with non-convex objective and non-convex constraints. It looks hard, but if we look deeper into the constraints, we'll see that if we concatenate them into a matrix form, the constraints basically require the matrices, the global and local PCs, to be orthonormal matrices. And all the orthonormal matrices, they form with a certain shape, they form a certain manifold called Stifel manifold. And to solve a constrained optimization problem on Stifel manifold where the objective is differentiable, we can use Stifel gradient descent. So can we use Stifel gradient descent to solve the problem? Probably we can. And also, as the objective here has a summation form, we can even distribute the objective into n different clients, where each client will only calculate the Stifel gradient contributed by covariance matrix SI. Okay, so this is the very simple form of our algorithm. I use gradient descent to update the parameters and send the updated copies of the global PC to the server and ask the server to take average. This looks viable, except for a small problem that after server calculates the average of the global PCs is no longer orthogonal to the local PC. So the variables become infeasible. This becomes an issue because it no longer stays on the Stifel manifold. So to solve this problem, we introduce another notion called generalized retraction, which will retract a general matrix into an orthonormal matrix. It has a definition, but basically we can prove that polar projection is a generalized retraction, and QR factorization is also a generalized retraction. Okay, and we can add this, bring this notion of generalized retraction into our federated iterative algorithm and add a modification. So in the updated, in the modified algorithm, in each communication round, the client I will receive an update from the server and use it to correct its local PC. And this correction step involves deflation and retraction, generalized retraction. And then it can safely use the corrected global and local PCs to perform a step of Stifel gradient descent. After that, it can send the global copy of the PC to the server will take the average and retract it again. This process repeats for multiple steps until convergence. It's worth noting that during the entire process, only the global PC are sent to the server. The data remains on the client, which means this algorithm is fully federated and it inherits the benefits from federated learning, such as savings in communication, distribution of computation, and preservation of privacy. Okay, the problem has a good convergence guarantee that says if the algorithm is initialized properly, the step size is chosen appropriately, the algorithm will converge into the ground truth, into the optimal solution at a linear rate. The rate is dependent on the step size of the minimum eigenvalue and also on the misalignment parameter. One can see that when the misalignment parameter theta is larger, the algorithm actually converges faster. This is in contrast to the standard federated learning algorithm, which usually converges slower when the data distribution is more heterogeneous. But in contrast, our algorithm will converge faster when the data set is more heterogeneous. This is a result of our explicit modeling of heterogeneity in the dataset through the local PC. Okay, so let's look at a few numerical examples. First, you may remember this graph a few slides back. On the right, those arrows are actually learned by our algorithm. They are the result of our personalized PCA algorithm. You can see that both the global PCs and local PCs correspond to the data patterns pretty well. And we also use an example to run our algorithm and plot the logarithm of reconstruction error versus the number of communication round. We can see that for multiple instances shown here, they all exhibit linear convergence at the end, which is consistent with our theoretical prediction of linear convergence. And also the bluer line indicates the theta is larger. We can see that the line is also steeper, which indicates the convergence is faster. So larger theta means faster convergence. This is also consistent with our convergence theory. Now let's look at a real-life example, video segmentation. You may know that video consists of multiple frames, and each frame, if it's grayscale, naturally corresponds to an image whose dimension is the resolution of the image frame. Okay, so we can view the video clip as multiple images, and each image represents a data set. They contain some similarities and they are also heterogeneous. The similar part, the global part shared by all the image frames, usually correspond to those stationary backgrounds, while the local parts within each frame usually correspond to the moving parts in the video. Here's an example of the video segmentation. We download a video from the internet, which is about a cat moving in front of a camera in the room. And we apply our personalized PCA on this algorithm, on this video to recover the global PC and local PC. We can see that the global part corresponds to the stationary background, the setup in the room, the furnitures, and the local PCs accentuates the moving cat. This application on video segmentation has its implications in additive manufacturing, where we use the personalized PCA to analyze the thermal videos that we capture in the laser-based additive manufacturing process. And we actually find that the local PCs correspond to the anomalies in the manufacturing process. So if we identify a very bizarre normal local PC with a very large signal, we are very likely to see an anomaly at this frame, which can correspond to mechanical defects in the printed objects. And this is a comparison between the personalized PCA with robust PCA, which shows when the differences between different frames are not sparse, then personalized PCA can do much better than robust PCA. Okay. Another application of personalized PCA is in the language data set. Here we analyze the presidential debate within the last 60 years, and we try to find the common words and unique words. To do that, we simply use the one-hot embedding of each word in the vocabulary and build a matrix for the debate corpus for each debating year, election year. Okay, and then we apply personalized PCA on the matrices and try to identify the common PCs, the global PCs and the local PCs. Global PCs are the common words, local PCs correspond to the unique words. We can see a transition in the debating topics from the local PCs for the recent 60 years in terms of domestic fiscal policies, international diplomatic relationships, education reform, law enforcement reform, etc. And for the common words, we can see that most of the presidential debates focus on tax. Okay, it's an interesting observation. And we have also extended our work in matrix factorization, matrix completion, and tensor data. In matrix completion, we can extract the shared, the global features and the unique, the local features of matrices that contain missings. And on the tensor data, we can also find the global component and the local component. Here is an example of an application of our methodology on the solar flare detection. So it will detect the abrupt solar activities, which usually correspond to solar winds. Okay, here's a conclusion, a short summary of the talk, and this is the end. I hope you enjoyed the talk. If you're interested in any method presented in the talk, you're welcome to scan the QR code and refer to our paper. Thank you.